answer if you want.
Yeah. Where will you see the questions?
Switch off the phone.
No, that is what they already sent to us.
This list is there already.
No, but suppose if someone is typing the questions.
I want to see
online,
the questions. I forgot.
For some reason it's not expanding.
Yeah.
So you can just pull down this upper part. Yeah.
This list is there.
No, but
I want to see the questions. Okay, so let me answer that question first. Where is the question? I wonder.
But if say now someone asks some questions, we see that.
This question is- Here, look. If it is there, it will come. Would you like to start? So I can just start talking. Okay, so there was a question sent by what's the name? By go to shovik@gmail.com where Shovik Sadhukan, yeah, okay. In Ising model, how to add a magnetic field. And so what you do is you have the Ising Hamiltonian, which is minus G summation SI dot SG, right? And to that, if you add minus B, B for magnetic field, summation SI. Why? Because every spin,
You continue.
every spin basically when it aligns with the magnetic field, so Bi into Si, so suppose there's a spin and there's a magnetic field which is also pointing in the same direction, then the energy will be lower, or there will be an energy contribution of minus Bi Si, right? Whereas if the spin is in the opposite direction and the B is in this direction, then basically the energy cost will be minus B dot Si, so that will be negative. So plus, effectively plus B Si, and that will hold true for each spin, right? Each spin in the lattice. So if some spins are pointing up, they are going to contribute minus B into the spin state of that. I mean, assuming that you have the B is pointing in the up direction, and then that will contribute a minus B SI value being 1 to the energy. Whereas if those spins which are pointing opposite to the magnetic field, they will have energy cost, they will add energy cost Bi Si plus Si being 1 to the energy cost, and that you have to incorporate when you do your metropolis attempt to flip a spin. So the energy change corresponding to the B has to be incorporated. Now, what is your second question? I think if we plot the exact and numerical solution, but that's a differential equation question, right? That's still not released. We'll answer this later. Any more Ising model question? How can we find the scaling factor? What is the scaling factor alpha beta? Are you talking about the critical phenomena? Which scaling factor? I can't understand. Local error of RQ4. I think differential equation part has not been released. I'll answer this later, not in this one-to-one, whatever this is called, interaction. Okay, so now the question is by K Subhasini, and the question is regarding assignment number 4. Where and how do we incorporate KBT in the code to compute the instantaneous magnetization per spin and instantaneous energy per spin? Uh, Okay, and so basically, if you remember the 2D Ising model, which you have already seen, set KB equal to 1, and basically what is happening is, in the metropolis update step, right? You flip a spin, then calculate the energy. Well, you calculate the initial energy and the final energy, and then if the energy increases of the system increases due to the flip, right, then basically you would see you have to calculate delta E, and the probability of acceptance is decided by delta E by T. I have not written KBT because KB equal to 1, I have written it just T. So when you do the 3D Ising model, it will be very similar to the 2D Ising model calculation, except in the 2D Ising model calculation, you have 4 neighbors. The 3D Ising model and a cubic lattice, you will have 6 neighbors. The rest of the thing, the calculation, including the point where T will go in, will remain the same. It's basically delta E by KBT, which is the Boltzmann factor, right? And that's all that is there to it. I hoped I answered the question. It's not very different from 2D Ising model. You have also asked, despite writing a code to compute the energy in initial configuration, could not get the relevant answer. Uh, okay. Well, we can't debug the code. The part of the learning process is to figure out, develop the algorithm, write down the code, and figure out where your error is. Basically, that's the process of debugging, right? When you write a code, you make an error, and one has to learn to debug. If you are asking somebody else to debug your code for you, then I don't know. I don't know how to. Then that's not basically there's no learning for you. You're writing something, there's an error, and you need somebody else's help to debug, which means there's an error in the algo or in the syntax. It's for you to figure that out. If you want me to discuss this again, so I think if it's a bug, you have to figure that out. I think that's the primary thing. Then what's the next question? Okay, so this is for Prasenjit. The next question is for Prasenjit, so he will take over. Shall I sit to the side? Any problem?
Okay, no, that's fine. So in the assignment number 3, so question number 4 was, so you were given an integral. Maybe I just write down the integral. Okay.
I think that will be better. Move ahead. Yeah.
Oh, okay. Maybe just. Okay, so the spin is. Yeah, okay. So what you were asked in that question was to evaluate this integral minus infinity to plus infinity. It's a 2-dimensional integral. E to the power minus x plus y by mod x minus y dx. Where is that? Okay, I go back to. So okay, anyway, so this was the integral which was needed to evaluate, and the question was what should be the good choice of the distribution of random numbers that you will use to evaluate this integral. So if you look at this function, so the numerator of this function, this term, this has an exponential form. So what it tells is that the function will have a significant amount of non-zero values in a small region in space, and in other regions it will be zero, and it will decay more or less in an exponential fashion. So in this case, you need to choose the exponential distribution. So you start with your random numbers which has a uniform distribution, convert them into an exponential distribution, and then use that newly converted distribution to evaluate this integral. Okay, now the can we go back to the question? Okay, and another one is question number 5. So let's see. Okay, so yeah, just so in case of question number 5, so again, if you look at the function, so I'm just writing down the function. The function is the form of x to the power minus 1/3 plus x by 10. So if I look into this function, so and if I divide this function by x to the power minus 1/3, so what I will get is 1 plus x to the power 1 minus 1/3, that will be 2/3 by 10. Okay, so this is what I will get, and so what this tells me is that I mean a good choice of the. I'm sorry. Okay. So a good choice of the probability distribution function will be something which has this form, x to the power minus 1/3. So that's why the correct answer is answer number 4. So I don't, let me see if there are any more questions. Okay, so the next question is by Rajan Bhuvan. So the question is, can Python or any other language replace Fortran for scientific computing? So the answer is okay. There is no clear-cut answer for this. So in general, from our experience, from our experience, programs like Fortran or C, they are much faster when you do numerical calculations for enormously large systems. So you may not see the difference between Python or any other language for with when you compare with Fortran for small codes, but for large calculations when you need to do, say, for example, millions of matrix diagonalization and then several integrations. So when you're really doing enormous realistic calculations, then you can see a difference between Fortran and Python. So the major difference between how these two codes work is the way you, the compiler reads the program. So in Fortran or C, so typically what happens is in the beginning, the compiler reads the whole program and then converts it to a language which is understandable by the machine. While in case of Python, programs like or languages like Python, it's done in a step-by-step fashion. For example, the compiler reads a line, then interpret it, and then execute that line. So that slows down the whole thing. So maybe, so as of now, okay, it's my personal opinion, but people might differ with that. But I think Fortran or C will still be the scientific choice of scientific computing. Okay, so the next question is maybe Apratim.
So I was just checking up. I faced similar questions in class, and I was just checking up the internet, which you can do independently, and compare the performance of Fortran and Python for serious number crunching. And so on NASA website it says a difference of speed of 8, But for many serious number crunches, the difference in speed is 100, which means calculation which will take 100 day using C or Fortran. Calculation which will take 1 day using C or Fortran could take up to 100 days. But it really depends upon the kind of problem you are doing, right? So
Okay, the next I mean, the same person has commented that the lectures for week 4 and 5 are hard for a person who is still learning Fortran. Okay, I mean, we understand that this is hard part, but I mean, unfortunately, we can't deal with that.
it's not a programming course
It's
anyway.
yeah. I mean, if you don't know programming, then you have to get yourself up to that level. That's the only thing we can say. And then there is also a request to include explanations for the assignments after the due date is over. Okay, so that we will do. We will do from maybe from the next time onwards. We will upload the solutions to the assignments which we are giving.
I mean,
Weekly assignments.
are we showing the codes?
No.
That's the
After
correct answers.
the assignments are not writing codes, right?
Yeah.
Okay, then in that case,
No, Ising model have to implement it in 3D.
no, but then what do they? What are the
So
answers?
I asked what is the average value of the magnetization for this temperature or something. What is the average value of CV?
Yeah, in that case, I don't
can
know.
tell them the correct answer.
You can tell them the correct answer and explain how it has
Yeah,
come.
maybe.
That is, and then I was not able to code for some questions in week 4. Okay. So this we can't help much, right? I was.
No, we can set. They are asking for books.
No, not books. So this I was not able to.
We're
code
showing
this.
them the codes. I don't know what's the problem.
So the codes we are showing in the lecture itself. So maybe what you can do is you can pause that part of the lecture,
Yes.
go through the code and try to compare it with what you have written and try to see. Okay, regarding the books, so there are a few books which you can refer to. So for example, maybe I just write down the names of the books. Okay, just delete everything. Let me just check the pin. Okay, so there is one book called Computational Physics by J M T H I J S S E N. Then there is another book. So this is on Fortran. So by S. Chapman. Also, there is another Fortran book by Rajaramanna. Rajaraman, sorry, not Raman. And then there is another one by Metcalf and Reed. So you can pick up any one of these books and start referring to.
For Ising, you want to call the
Yeah,
sure.
So then there is the numerical recipes book. Which are available for both Fortran and C. So this book actually contains several subroutines which has implemented different methods which we have discussed. And the authors are by W.H.S. S.E. Teulsky, and so there are two more authors. So this is basically, so I'm not writing the whole name. This is Cambridge University. Publication. Then for your Ising model stuff, what you can refer to is there is this book called Computer. No, this is for molecular dynamics, right?
Yes.
So this is for molecular dynamics, sorry, computer simulations of liquid by
Allen.
MP Allen and DJ Tilsley. Tilsley. Okay, and then there is another book which covers a large range of simulation techniques. It's Understanding Molecular Simulations. From algorithms to applications. Frankel and Smith, right? So how do I go to the next page? I just delete it. Okay. Then, so for your differential equations or Schrodinger equation, which you will see in the later part, that is basically numeral and variational principle. So I have taken the materials from the course materials of this guy, Paolo Eolo Gianozzi. So you can search for his web page and you will find that. Also, you will find in the Thijssen's book on computational physics these techniques, computational physics by Thijssen. That is the first book. THIG. Okay, I'm sorry about the spelling. So that is the first book I mentioned in the previous page. And for your
DeFries and Hasburn.
Okay, why don't you?
So for differential equations, the name of the authors is. Oh. This is the name of the authors and Hasburn, and it will be named something like computational physics. And for Monte Carlo, the book is by K. Binder and Heerman. There's also one by D. P. Landau. And K. Binder, both on Monte Carlo simulations. I hope this answers the question. It is also, I think, available. This list of books is also available
in the course.
in the course details or description. Sorry. So, any other questions?
No, I just want to make one. Okay, let's go back to the questions list.
Ah, so let me go back.
No, I think the rest are all your. Okay, there are a lot of things.
This is the one to give you last.
Yeah, so but before that, let's finish this one. Okay, so for you, this is another Ising model. No, before that, this question.
In Ising model, when the initial energy is computed along according to the neighbor lattice, why is spin ji used instead of spin ij? Actually, if you look in that loop when I'm calculating the initial energy, so the loops that I've written is do I equal to 1 to j, y equal to 1 to l, and then do j equal to 1 to l. So the inner loop, the more fastly varying variable is j. So that actually helps in a faster code. Now you won't notice any difference in speed in this particular 20 cross 20 or whatever the small lattice sizes. So there's no great deep physics reason. It's basically that in Fortran, the inner loop should be on the left hand side in a multidimensional array. In C, the inner loop, the index, the variable of the inner loop should be on the right hand side. It's related to how data is transported from the RAM to the CPU. Okay, so even if you did the entire calculation for your case, where you wrote spin ij and also the RHS of the equation, you wrote corresponding, made the corresponding changes, you will get the same answer. It doesn't matter, it's a matter of speed. Okay, so that I don't want to discuss now.
Okay, okay, so then there is one more. This one. Since we are now having to plot our data to interpret many results, can you please elaborate on the bit of such softwares? Maybe one particular sector and this crash course and how to use it.
Okay.
So
New plot, XM Grace.
I think XM Grace will be
XM Grace will be
easier.
very similar. If you closely observe when I plot the data, okay, most of the cases actually I
Because GNU plot you need to go into.
yes. Um, so we haven't prepared lectures for them, but XM Grace is a very simple software to learn. If you have data written in columns, you can plot column 1 versus column 2 versus column 1, column 3 versus column 1. So the plots that you have seen in the lectures is basically XM Grace, right? And yeah, just look up any tutorial on XM Grace on the web. I think that is the best thing. I mean, it's difficult to have a few lectures on uploading software, I think.
Okay, another.
In one case, in the differential equation case, actually I have made some movies, and there I have taught how to make the movies actually. But for the Ising model, there's a case where I'm showing a movie that I have avoided teaching you how to make the movie. But data plotting you can do using XM Grace or anything of your choice.
Okay, so another comment which I want to make was when we are talking about random numbers in the lectures. So one comment which I made was every time you need to generate a new series of random numbers, you need to use the random underscore seed subroutine, and that is true for the older versions of G Fortran at least I know that that is true for now. But in the newer versions of G Fortran which are there, so there is an inbuilt seed already in the subroutine which is generating the random numbers for you. So that's why when you are every time when you are running your code, so some of you got different random numbers, different sets of random numbers. So that is the reason why you are getting. So in the latest version of Fortran, basically there is already a inbuilt seed generator for you. You don't need to worry about it. Okay, so I can see some questions here. Last question from assignment 4.
I don't have it ready.
Please.
What was the last question?
You don't have the assignment 4.
Well, I can look up. Yeah, I have that.
Okay, we can take that later, but so this one you can talk. So here, these questions we just explain, or we need to type the answers. Okay, so Sovik Shadu Khan has a question: how to calculate spin-spin correlation factor for Ising model? Please help me with the code. Apratim for you.
A spin-spin correlation function is basically calculating the spin at a certain position ij, and then you multiply it with a spin at a distance r, where r is a variable, and calculate its statistical average. Okay, so I mean, just to do it spontaneously was a bit difficult, but spin-spin correlation function. If you look up your Monte Carlo book by Kurt Binder, there it is given in great. Kurt Binder and Herman or D.P. Landau, there it is given in great detail. Okay, so yeah, so in a 2-week course, I've avoided discussing about correlation functions and so on and so forth. Okay, so you have some question. I will look up what is the last question.
So the question is, what is the best editor to write Fortran code? Again by Sovik Sadhu Khan. So okay, I mean I don't have a definite answer. I use GVIM.
Same here.
Yeah, it depends on the choice. So for VI, you need to know some commands. So sometimes it becomes a bit uncomfortable. But with GVIM, it's like a Word document. So you can just simply. That is one simple thing. There are some sophisticated ones called Emacs. You can use that, but I haven't tried it myself, so I don't know what is the thing. Okay, so there is the question by Mahesh Shinde. So I didn't. So what is the question? I don't understand. So you want to find out the integral for this, or what?
Assignment 4, he said, right?
Then Mahesh Chinde has asked another question: how does the radius of gyration of polyelectrolytes vary with the light scattering intensity? I don't know how this is related to computational physics, so I don't know.
Please read up the relevant papers. This is not part of the course.
So yeah, assignment 4, last question.
Yeah, what is the question?
Programming related parts are remaining unclear.
Which is the question? Where?
This one, Ria down.
I'm learning a computer programming course and coding related the first time in this paper. See, this is not a programming course, this is a computational physics course, right? If you can pick up programming, so here we are not discussing programming languages and so on. It is and anyway, I mean, we show you the entire code. In IISER, we just tell the algorithm and the background physics, and the students develop the algo on their own. Okay, so I mean, I don't know, I cannot. Programming related parts are remaining unclear. The algo is told, the programming is shown, I don't know what else can you do. Last question from assignment 4. Well, I calculate instantaneous spin in 2D Ising model, right? In the 3D Ising model, you just have 6 neighbors instead of 4. The rest of the calculation goes as similar. So, just the way I'm calculating instantaneous magnetization per Monte Carlo step. In the 2D Ising model, you have to do exactly the same thing for the 3D Ising model, except now instead of 4, you have 6 neighbors. So you have to incorporate that. So we have to incorporate that in the periodic boundary condition. You have to incorporate that when you are calculating energies, and that's all that is there to it. So you have to change the code to 4 or 5 in 3 or 4 places, basically. Yeah. Anything else? I think we are done.
Let me just put questions. So there are, I mean, we have answered this now. So what do we do? We wait for 20 minutes or just?
Say
Okay,
thank
so
you and
just say.
thank you.
Maybe also you can say thank you.
Okay, so thank you.
No, okay. Okay, so since there are no more questions, so we are just closing this session. Thank you for attending this.
Thank you.
Done quickly.